Hey chemists, how you going? This is part two of our polymers video. This goes with the second notes document as we go through, so make sure you're filling that in as we go, pausing the video as you need. So to start with, we're going to look at advantages versus disadvantages of synthetic polymers, so produced by us. So the advantages of synthetic polymers are they're cheap, they're tailor-made, so we can make them to suit any purpose we want. They're malleable, so you can change their shape, and they're also colorful, so children's toys, you can use them in lots of bright colors that can appeal to lots of different people. The disadvantages that everyday people probably don't take note of all that often, they're petroleum-based products, so we need to actually derive the products from petroleum, so we need to distill them. So that's not good in terms of utilizing a fossil fuel. Most of them aren't biodegradable. We can see the plastic pollution. There's lots of movements going around picking up rubbish. You can see there's lots of actual places and attractions that have been really damaged by the uses of plastic, the overuse of plastic, and that a lot of it makes its way to our oceans and natural environments. Many of them are buried as landfills, so we're talking about big rubbish tips. They have chemicals added as well in order to add to their properties. So these chemicals that are added, when they burn, they produce toxic fumes, so that's not very good, and they can leach harmful chemicals into soil and water. So over time, those chemicals can be leached out of the plastics, and it can affect the aquatic environment. So what we're going to go through here is look at some addition polymers. An example that we're looking at is rubber. This section here, natural polymers condensation, was covered in organic chemistry. Synthetic polymers addition and condensation was covered in the previous video. So natural rubber. So this is the polymer of natural rubber. So we've got our repeating unit here. We can see that we're alternating between carbon-carbon single bonds and double bonds. So the repeating unit is a bit more complicated than normal because you need to notice the fact that you've got single, double, single, and then also look at the substituents. So you can see that methyl group here. So the first question that we might be asking if you come straight from the previous video is, wait, how can a polymer have double bonds in it? Because when we did addition polymerization, all those double bonds were turning into single bonds. So it's a bit trickier because the monomer has two sets of double bonds. So this is the monomer here. Can anyone name this molecule? I've got the answer down the bottom here. My face is covering it, but it's 2-methyl-1,3-butadiene. So we've got two ethyl groups. Ethene functional groups, carbon-carbon double bonds. So it's a diene, and we've got a methyl functional group coming off of carbon 2 there. So two sets of double bonds. So when it undergoes that addition reaction, only one double bond is going to form the single bond to link with the others. So basically how this works, we've got a pair of electrons here. So basically the double bond, so it's going to move to accommodate the electrons. So basically this double bond is going to shift over here. So this is movement of electrons. So this mechanism is a bit complicated. It's probably getting closer to university level chemistry, but we've got the double bond moving over here. And then this double bond is moving, and those electrons are moving there to link with this second monomer here. And then that's doing the same thing, moving. So basically that double bond is shifting, and that double bond is shifting to form a new bond that is going to link these monomers together. So you end up with the polymer here. So that's why the rubber polymer has double bonds. You may have been surprised that rubber is not synthetic. Rubber is actually a natural substance. You might want to look up where rubber actually comes from. So I've got a bit of an example here, but you might want to have a look at what those trees look like. So it's sap from certain trees. Latex is untreated rubber, which is inelastic. And if you heat rubber with sulfur, it becomes elastic. So if we add a different chemical to it, it changes its properties. And we need to show how this happens. So basically, this is our rubber polymer, a simplified version. We've got that carbon-carbon double bond there, and then that's the rest of the monomer there. So this process, by adding sulfur and heating at high temperatures, is called vulcanization. So we've got some Star Trek stuff going on there, the Vulcans. So vulcanized rubber is adding what's called a disulfide cross-link. So a cross-linkage, which we learnt about in the previous video. So it's covalent bonds that are connecting these polymer chains, and they've got sulfur atoms, so they're called disulfide, two sulfurs, and you've got those cross links there. So you notice that when we're adding them on there, because those covalent bonds are connecting to that carbon, the double bond is going away and forming a single bond because we have to keep with that covalency of 4. There's another hydrogen atom there that hasn't been shown. So basically, everywhere there's a carbon-carbon double bond, those disulfide crosslinks can add. So this is an example. Here's our rubber polymer, and we add our sulfur and we heat it at high temperatures, that vulcanization reaction, and then we get disulfide crosslinks here. This is a trisulfide crosslink, and we can see that that's connecting those polymer links together. So that's cross chains. So it was invented by Charles Goodyear. So you probably have heard of Goodyear tires before. Essentially, this happened in the 1800s. Accidentally dropped some India rubber mixed with sulfur on a hot stove and discovered vulcanization. So it was basically cooking and ended up with something that was very, very tough, rigid, resistant to heat. And that's the material that we made the tires from. He was granted his first patent in 1844, but had to fight numerous infringements in court. The decisive victory did not come till 1852. So then he could patent his mixture to create tires. You can control the amount of sulfur, so that can change the different properties of tires depending on what kind of car you have, the road surface conditions. If you're into cars and you're going to be buying tires, spending money, you'll learn more about that. If you've got a small amount of crosslinks, they're elastic. If you've got lots of crosslinks, they're very, very hard rubber like ebonite. So vulcanized rubber is harder to recycle because it will char and you have to get rid of the sulfur. So polymer production, most polymers are derived from petroleum-based products. We need a more environmentally sustainable production of polymers. So this is where synthetic biopolymers comes in. So that prefix bio is always referring to renewable materials being used as opposed to petroleum-based products, which are fossil fuels, which are considered a one-time resource because they take millions of years to form. So various polysaccharides, proteins, and triglycerides can be used in the production of synthetic biopolymers, which are derived from renewable plant-based material. So the advantages and disadvantages of production from petrochemicals. So we're talking about polymer productions here. So petrochemicals, petroleum. So the advantages, we've got lots of petrol and natural gas. So there's lots of it there. It's easily extracted and processed because we have the infrastructure. The industries exist for those products. So basically people want them. There's a wide variety of polymers that can be derived from those petrochemical feedstocks. So feedstock is talking about a chemical that we make other chemicals from. So the disadvantages, petrol and natural gas reserves are being depleted very quickly because we're using them for so many different things. The rate of depletion is much faster than the rate of formation, so we're going to eventually run out. And it's non-renewable feedstock, which is basically kind of similar. All of these are pretty closely linked together. So production from biomass, so renewable plant material. The advantages, carbohydrates, proteins, oils are abundant feedstock. We've got lots of access to these. They're easily extracted and processed just like the petrochemicals. The source can be a byproduct or waste product for some other industries. This is really important. So basically other industries have this renewable plant biomass material that we can use in order to make these polymers. We just need to set it up so it's happening, it's sustainable. It's basically the startup that's important. Renewable feedstock, so we can grow more plants, and that can happen again and again and again. The disadvantages are, at the moment, there's only a limited range of polymers, so we can only make a few of the many different types of polymers that exist. And the competition with land crop for food is there. Now, in Australia, we've got lots of available land. That's not the case for lots of different areas in the world. So degradable polymers, they're designed to maintain structural integrity and functionality and then break down over time in the environment after disposal. So you can see the benefit of this. So while they're existing, they're good. They do exactly like regular polymers do, but they're biodegradable. So they're going to actually break down as opposed to living in the environment for hundreds of years. They can degrade due to microorganisms, hydrolysis, oxidation, and absorption of sunlight. So these are the different conditions that can break those down. So if we've got polymers that can be degraded by microorganisms, they contain enzymes that degrade polymers. Bacteria, fungi and algae are examples of these. So basically within them, they've got enzymes that work to break those down. If you've got polymers with amide and ester groups, that's broken down by natural hydrolysis. So we know that those are created via condensation reactions. So hydrolysis reactions, which is where water comes in, will degrade them over time. So these actually break down better. Oxidation, i.e. the double bonds in rubber, ozone breaks the crosslinks. So if we've got the ozone chemical, we've got some oxidation that can happen. Also, absorption of sunlight, photodegradable, it means the natural sunlight will break down that polymer. And we're done, guys. So that's polymers done. Hopefully you got something out of this video. Bang on 10 minutes. I will see you next time.